Step inside a luxury glass penthouse in Dubai, and the air is perfectly chilled. Step outside near the ground-level mechanical exhaust, and you are hit by a wall of heavy, humid air. Dubai does not destroy heat. It simply relocates it. Every perfectly cooled room requires that heat be carried somewhere else, pushed out into the city's streets and atmosphere. To sustain this artificial climate across the Gulf region, projections suggest that continued conventional cooling patterns could require approximately $100 billion in new cooling hardware by 2030. That is not the value of one Dubai utility, but a regional estimate that also includes more than $120 billion in associated power supply capacity. Where does the heat removed from an entire skyline actually go? The physics of air conditioning are completely unforgiving. You cannot make an interior colder without making the exterior hotter. The heat removed from inside, plus the energy used by the machine itself, equals the total heat that must be rejected into the surrounding environment. The colder the interior is maintained, the more heat the system must continuously carry away. Now multiply that simple thermodynamic invoice across an entire financial district. Beneath Business Bay, there is a buried network that resembles blue arteries supplying the towers above. This is district cooling. Instead of every tower relying entirely on its own isolated cooling plant, cold water is produced centrally and circulated to multiple buildings. The scale of this coordination is staggering. One connected project in Business Bay serves 188 multi-use buildings and skyscrapers. It relies on approximately 52.4 kilometers of underground distribution network. The operation requires 9 planned plants, with 4 already operational when the project announcement was published in 2024. That same announcement reported a connected capacity of 241,272 refrigeration tons. That unit conceals the actual thermal scale. As an illustrative capacity conversion, 241,272 refrigeration tons is equivalent to approximately 849 megawatts of connected cooling capacity. This is a mathematical unit conversion, not a real-time load measurement of heat being rejected at any single second. But it reveals the sheer size of the industrial infrastructure required to keep the glass towers comfortable. At first glance, a system this massive might look like the ultimate example of urban excess. The most inconvenient fact for critics of Dubai is that this sprawling, buried machine may actually be the better way to cool a desert city. District cooling is not necessarily a foolish engineering choice. Official statements from Dubai authorities claim that district cooling can reduce cooling-related energy use substantially. Some claims highlight energy reductions approaching 50% compared with conventional standalone systems. A centralized plant can support massive thermal storage and optimize operations in ways that an isolated rooftop chiller simply cannot. But that efficiency evidence does not destroy the argument against the city's thermal model. It makes the argument much more disturbing. Even the most efficient cooling solution on Earth cannot abolish heat. It can only move heat with lower energy input. The machine is not failing. It may be working precisely as designed. The uncomfortable detail is that the city has been constructed so that the machine must run constantly just to keep the buildings habitable. After the sun sets, the city reveals what happened to a massive portion of the day's heat. A 5-year study measuring Dubai's canopy urban heat island found that the average urban air temperature was approximately 1.3 degrees Celsius above the rural reference. More critically, the average nighttime urban heat island intensity was approximately 3.3 degrees Celsius higher. Air conditioning does not create this entire temperature difference alone. The heat island is driven by artificial surfaces, stored solar heat, urban geometry, and reduced wind flow. But the mechanical heat rejection operates inside that altered environment, adding a continuous flow of hot exhaust to streets that are already struggling to cool down. This creates a relentless loop. Solar radiation bakes the glass, walls, and roads. Heat enters and accumulates inside the heavily glazed towers. Cooling demand rises, forcing the equipment to consume more electricity. Both the indoor heat and the operational energy used by the chillers must be rejected outward. The dense urban materials continue releasing stored heat after sunset, ensuring the system must work harder the next day. Electricity is not the only network required to carry this heat away. The polished luxury interiors depend heavily on another hidden flow beneath the city. Look at the visual contrast between two climates existing mere meters apart. Inside, there is polished stone, sealed glass, quiet hotel corridors, and perfectly controlled humidity. Outside, delivery riders, security personnel, and maintenance workers navigate radiant pavement while searching for shade near mechanical service entrances. Cooling does not distribute equal relief from the heat. It distributes the ability to escape the heat. Research analyzing everyday life with air conditioning in Dubai found that while cooling is ubiquitous and central during hotter months, it is not equally available or experienced across all socioeconomic groups. Has the city defeated heat, or has it simply decided who can remain separated from it? A marble lobby is not inherently cool. A glass tower is not naturally comfortable. Those conditions are continuously delivered through electricity, chilled water, heavy pumps, heat exchangers, and maintenance teams. Luxury is not embedded in the building materials. Luxury is a service being continuously delivered to those materials. What remains when that service pauses? Thought experiment, not a prediction. Imagine a major chilled water circulation network in a dense district is temporarily interrupted during an exceptionally hot and humid period. There is no explosion, no terrorist framing, and no immediate citywide blackout. The chilled water lines on the map simply stop moving, and the sound of the pumps disappears. Without cold water carrying heat away, the physical consequences begin immediately. The heat does not need to break into the building. It is already entering through the glass and walls. Occupants, lighting, electronics, elevators, and commercial kitchens continue adding internal heat to the sealed spaces. Indoor temperatures begin rising. Operators must prioritize systems and adjust occupied spaces. Hotels alter their operations while apartments continue to gain heat from the afternoon sun. Normal operating margins begin shrinking rapidly. How many other urban functions quietly assume that cooling will remain available? Cooling is not one optional utility operating beside the city. It is woven into the operating assumptions of the city itself. But we must end the thought experiment and return to a cooling plant operating normally. The pumps are running, the water is moving, and the control screens are stable. There is no visible crisis. The central story is not what happens when the cooling machine fails. The central story is what must happen every single second to prevent failure. The system is working exactly as designed, and that is the trap. To understand how this continuous delivery works, you have to follow one unit of chilled water through the system. It begins at a central plant where industrial chillers lower the water temperature. Massive pumps then push this cold water through a vast network of insulated underground pipes. It travels beneath the roads, forming a subterranean circulation system until it reaches an energy transfer station serving a specific building. Inside the tower, the chilled water absorbs heat from the building's internal mechanical system. This heat could come from a luxury apartment, a busy restaurant kitchen, a crowded shopping concourse, or a quiet office floor. The chilled water does not touch the indoor air directly, but it acts as a thermal sponge. Once it has absorbed the internal heat, the warmer water returns to the central plant through a parallel return pipeline. The absorbed heat passes through the plant's heat exchangers. The water is chilled once again, and the massive pumps send it back out into the network to begin the cycle all over again. The control room sensors must constantly monitor flow rates and temperature differences to balance the thermal load across dozens of towering structures simultaneously. To manage the enormous power required for this process, operators use thermal energy storage. Large insulated tanks store chilled water produced at night when electricity demand and ambient temperatures are lower. This stored capacity is then dispatched during peak daytime hours to help absorb the district's extreme heat loads. Every single step of this closed loop requires heavy industrial intervention and relentless monitoring. The district cooling model is a marvel of coordination. Efficiency reduces how much the system consumes. It does not reduce the city's need for the system to remain available. The scale of that unwanted heat is driven by the physical reality of building a modern metropolis in a desert. The heat load comes from three distinct processes that operate simultaneously. First is solar gain. Intense sunlight aggressively heats the extensive glass facades, flat roofs, concrete structures, and exposed asphalt roads throughout the long daylight hours. Second is urban storage. These artificial materials absorb radiant energy throughout the day, holding it deep within the urban geometry. Third is anthropogenic heat. Additional thermal energy is constantly generated locally by heavy transport, lighting, building activity, human movement, and the exhaust from the cooling systems themselves. This combination fundamentally alters the local climate. A 5-year study measuring Dubai's canopy urban heat island found a clear distinction between the city and the surrounding open areas. The study reported that the average urban air temperature was approximately 1.3 degrees Celsius above the rural reference. More significantly, the artificial environment struggles to cool down after sunset. The average nighttime urban heat island intensity was measured at approximately 3.3 degrees Celsius higher. Dubai effectively becomes a massive thermal battery. It charges with intense solar and mechanical energy during the day. It then continuously discharges that stored heat back into the streets and the lower atmosphere at night. Because the dense city materials store so much heat, the cooling demand remains exceptionally high long after the sun has gone down. The mechanical system is trapped in a loop where it must constantly fight the thermal mass of the city itself. Part of the system that carries this heat away begins with a resource Dubai cannot afford to waste. Many large district cooling plants rely on cooling towers that use evaporation to reject the absorbed heat into the atmosphere. This evaporative process consumes a significant volume of water on a daily basis. Using desalinated potable water at this industrial scale would create a massive resource contradiction in an arid environment. It would mean burning immense amounts of energy to remove salt from seawater, only to evaporate that fresh water to cool down buildings. Dubai recognized this vulnerability early in its infrastructure planning. A 2008 resolution from the Dubai Executive Council mandated specific conservation measures. The regulation requires district cooling operators to implement thermal storage and directs them away from using desalinated water for central cooling. Instead, it identifies alternatives such as treated seawater, gray water, and sewage water. In Business Bay, reports have confirmed that the district cooling plants utilize treated sewage effluent and thermal energy storage to operate sustainably. This means the cooling network depends entirely on another hidden infrastructure. Follow the water from its origin point. Wastewater leaves a building and enters the municipal sewer network. It travels to a heavy treatment facility, where it undergoes intensive processing and rigorous quality control to meet cooling standards. The treated water is then pumped through a dedicated distribution network directly to the cooling plants. There, it is exposed to the air in cooling towers to facilitate evaporative heat rejection. The polished hotel lobby and the sewage treatment system are not opposite worlds. They are deeply connected parts of the exact same urban metabolism. Solving one resource problem requires building, pumping, and maintaining an entirely different industrial flow beneath the city. Every perfectly chilled room is ultimately connected to a municipal wastewater pipe. The machine does not protect everyone from heat in the same way. Follow 3 people during the exact same summer hour in Dubai. The first is a visitor stepping directly from an air-conditioned vehicle into the vast, cooled atrium of a luxury hotel. The second is a delivery rider waiting for an order on an exposed service road, fully subjected to the intense radiant heat of the asphalt. The third is a mechanical technician entering a loud, humid plant room to maintain the exact system keeping the hotel atrium comfortable. Air conditioning is central to everyday life during the hotter months in Dubai. Research analyzing these experiences confirms that indoor life adaptation is ubiquitous across the city, shaping how people plan their entire day. But access to that cooling, the quality of the thermal environment, occupational exposure, and the freedom to leave the outdoor heat are highly unequal. Indoor comfort is a condition that must be continuously purchased through housing, transportation, workplace location, and access-controlled spaces. The massive infrastructure network does not eliminate thermal exposure for the entire population. It simply redistributes protection based on who can remain inside the cooled envelope. Which person is experiencing Dubai's external climate, and which person is experiencing a climate manufactured specifically for them? The luxury glass tower offers absolute thermal safety, but only for those who do not have to maintain its hidden machinery or navigate its hot perimeter. The mechanical system provides an incredible shield against the desert, yet it fundamentally divides the human experience of the city. Future heat will only increase the inherent value of this thermal protection, along with the immense financial and operational cost of maintaining it. The pressure on this entire system is guaranteed to rise. According to the United Arab Emirates' submission to the United Nations Framework Convention on Climate Change, regional climate projections point to a harsher baseline. The third nationally determined contribution document explicitly anticipates significant temperature increases, higher humidity, and extended hot and humid seasons. These are broad climate projections, not an exact daily forecast for a specific neighborhood, but the physical implications for urban planning are unavoidable. Hotter and more humid external conditions will directly increase both the difficulty and the duration of maintaining indoor thermal comfort. Return to the Business Bay District cooling network to see how the infrastructure is preparing for this escalating demand. The connected capacity reported in 2024 was 241,272 refrigeration tons. But the ultimate planned capacity for that exact same development is 451,540 refrigeration tons. That ultimate figure is approximately 87% above the recently reported connected capacity. This is a comparison between published capacity figures. It does not mean all of that additional capacity will operate simultaneously tomorrow morning. But it reveals the staggering scale of thermal machinery required to keep pace with an expanding skyline. This brings us back to the $100 billion figure that defines the region's cooling trajectory. That massive financial projection represents exactly what happens when population grows. Total floor area expands, indoor comfort expectations remain high, and the hot seasons lengthen. More machinery and more power generation capacity must be constructed simply to maintain the current standard of living. The hotter the future becomes, the more valuable artificial cooling becomes. And the more valuable it becomes, the harder the city is to operate without it. A larger cooling system may be necessary, but building only a larger system cannot end the loop. Breaking this loop does not mean switching off the air conditioning or abandoning every glass skyscraper in the city. It requires fundamentally changing how much heat the mechanical system must remove in the first place. Dubai already knows how to construct highly efficient, incredibly powerful cooling machinery. The harder task is constructing buildings and public spaces that demand less from that machinery. A realistic response requires a multi-layered approach to urban design. The city must continue expanding efficient district cooling networks where they make engineering sense. Operators must maximize thermal energy storage to shift power demand away from peak daytime hours. They must aggressively prioritize suitable non-potable water sources to protect the region's desalinated water supply. But the most critical interventions must happen before the mechanical cooling is even required. Future development must reduce unnecessary solar gain by designing facades intended for an actual desert climate, rather than a temperate zone. This means drastically reducing unnecessary structural glazing on sun-facing elevations. It requires improving building insulation and ensuring tight thermal envelopes to prevent cold air from escaping. Where the local climate and specific building functions permit it, passive ventilation must be supported. Permanent shading must become a foundational piece of urban infrastructure to protect pedestrians and reduce the heat absorbed by artificial surfaces. The size of the current cooling machine is not merely evidence of incredible technical ability. It is evidence of what the city physically requires in order to feel normal. Cold indoor air in Dubai is not a natural state. It is a product that is continuously manufactured. The immense heat and resource costs required to produce that cold air are not erased, they are simply transferred elsewhere. The infrastructure needed to sustain this comfort reveals the deep vulnerability of the city's urban model. Dubai's cooling system is not exposing a critical weakness because it is badly engineered. In many respects, it is highly sophisticated and remarkably efficient. But its sheer scale exposes exactly how much electricity, treated water, careful planning, maintenance, and human labor are required to make an extreme external climate feel completely invisible indoors. When a city needs an industrial machine this large just to feel normal, is the machine protecting the city, or is it revealing what the city has actually become? This documentary is for educational, analytical, and documentary purposes only. The information presented is based on publicly available engineering reports, environmental studies, regional climate projections, and published capacity data regarding district cooling networks. Only hypothetical scenarios discussed, such as network interruptions, are strictly for analytical stress testing and do not represent actual predictions of infrastructure failure. The content provided does not replace professional urban planning, mechanical engineering, or climate adaptation assessments. When a city relies on a machine this vast just to maintain a baseline of normal life, it forces us to ask questions about the urban systems we take for granted every day. How much of your own city's survival depends on hidden infrastructure that you never see? Could your local networks withstand the kind of thermal pressure that Dubai handles daily? Share your thoughts and local observations in the comments below. If this investigation changed how you see the engineered world, subscribe to Dubai Viral and turn on notifications so you never miss our deep dives into the hidden systems that run the modern metropolis.